Hi, we are going to talk about integration by parts. Integration by parts is going to be based on this formula here that you're going to be using for that. And basically what it is some kind of a substitution that you're going to use to put an expression into a form which will allow you to integrate that. What happens when you have to use this type of expression is when you are dealing with a problem when substitution does not work, like regular U-Substitution that most textbooks call it, or some other methods, and you're going to have to do it another way. So anything that is in this form, which is where U and V are two different expressions, two different functions if you want to call them, and then you can rewrite it this way. So let's see how this is going to work here. So in this case we're going to say that x is U, and then we're going to need to differentiate that. So dx is going to be du. That's pretty easy. The other part here, so this takes care of that. The other part here is sine x dx. So we are going to call that dv. So sine x dx is dv. And then when you integrate that, you're going to get negative cosine x, and that's going to give us v. Alright, so we're going to go ahead and rewrite using all that here. Rewrite our integral in this form. So it is uv, so it's x times negative cosine x minus the integral v du. V is negative cosine x and du is dx. So this integral here that you have now is a very basic one. You can hopefully integrate that without any struggle. So when we rewrite all that, that's negative x cos x plus sine x, and of course plus c. This problem is completed. A common question that students ask: how do you know which one is going to be u, which one is going to be dv? In this case it's a little bit easier because sine x, if you leave it by itself, it's going to be easier to integrate, and when you differentiate x, you are going to get 1. And this way it will eliminate that, so as in the resulting expression we don't have any x besides the one that cosine has. But you can always try it one way, and if it's not going to work, you can try it another way. There is no issue there. It does take a bit of a trial and error sometimes to get used to and become more comfortable with these types of problems. Let's take a look at the next example. So this one's a little different. We have ln x, and what makes it a little bit easier is because we do not really have a formula for integrating ln x. So that means that it seems to be natural to say that ln x is going to be u, and then you differentiate that. That's going to be 1 over x dx equals du. Okay, so this will take care of that part, and now we have to take care of the other stuff here. So this is x cubed dx. It is actually pretty simple because it's a polynomial expression. So we call it dv, and if you integrate that, this is going to be x to the 4th over 4 equals v. Okay, so we're going to substitute all that. We're using the same formula from the other page. So the first part is uv, which is going to be ln x times x to the 4th over 4 minus, and then we're going to have the integral. So v, which is x to the 4th over 4 times du, and that's 1 over x dx. So what's nice about this is going to turn out to be just a polynomial, and you can hopefully integrate that without too much struggle. So let me just rewrite that in a more traditional form. So it's x to the 4th over 4 times ln x minus, once you simplify it, this is going to give you the integral of x cubed over 4 dx, and then it should be easy to integrate this one. So we'll have x to the 4th over 4 times ln x minus, and this part is going to give us x to the 4th over 16, and then plus c. This problem is completed. Okay, Here it might be a little bit easier because if you would have made ln x dx as dv, you would run into a problem of not being able to integrate that. Unless you somehow know the formula for integrating ln x, but it's not really a textbook formula that you can just easily recall. Alright, this is where it gets a little bit more challenging because with this problem, so we are going to start the same way. We are going to say that, okay, so we kind of rely on our first example. So x squared is u, which means 2x dx is du, and then cosine x dx is going to be dv, which means sine x is v. And we are going to rewrite that, but you will see what kind of problem we're going to run into. So uv, which is going to give you x squared times sine x, minus the integral of 2x sine x dx. Here's the problem that we have here. The problem is that this integral here is the one that we're actually going to have to do this process with all over again. Why? Because it does have that x sine x. So what we're going to do now is we're going to repeat the same process for just that integral. And actually, I don't want to do that. If you want to do this, you can, but I'm going to refer to our first example where we actually integrated that. In our first example, we found that the integral of x sine x dx was negative x cosine x plus sine x, and then plus some c1. I'm going to call it t1 so I can finally merge all my c's together. Okay, so I'm just going to rely on that, and then of course these two here is just a matter of distributing. So my whole thing here, this is just something that I can use, but you would, if this is a problem that you did not do before and you don't have an answer for that, you just repeat the same process again for just this integral. But here's what we're going to get. So it's x squared times sine x minus 2 times negative x cosine x plus sine x plus c1, and then finally if I distribute everything, my answer is going to be x squared sine x plus 2x cosine x minus 2 sine x plus, and I'm just going to call it some general c. Okay, and that will be the answer. So can you repeat, if you need to, can you repeat integration by parts several times? The answer is yes. It just gets a little tedious, and you need some extra space to work problems out, because when you need to do that, you're going to need to do it separately for another integral, and then you have to remember to bring it all back together to finalize the problem. Okay, so remember this line here, I don't know what just happened, this line here is something that I recall from example 1, if you want to rewind back and take a look at that, and that's the answer that I used from there. Of course it was a little bit easier because this was already done. Alright, let's take a look at the next problem. So this one here, x times e to the x, is somewhat similar to the first one, but so x is u, and then dx is du, and then e to the x, what's nice about e to the x, it doesn't really change with integration or differentiation. I have something going on there, some kind of a noise, I apologize. So e to the x dx is dv, which means e to the x is v. Okay, so we are going to rewrite that. So uv x e to the x minus the integral of v du, so e to the x dx. And it sounds very nice. You're gonna love problems like that. X e to the x minus e to the x plus c. Okay. I do want to remind you that all these problems are going to be possible to check the answers by differentiating the answer to ensure that you are getting the integrand. You can use integration by parts for situations when you only seem to have one term. So in this case, I just have the integral of ln x dx. So there is really no choice here. Ln x would have to be u, which means 1 over x dx equals du. And dx by itself is going to be dv, which means x is v. Okay? So when I rewrite that, I am going to get the following. So uv, which is going to be x times ln x, minus, and here I'm going to have my integral of v du. So v is x, du is 1 over x dx. So this can be simplified. Going to have x ln x minus the integral of simply dx, or 1 dx if you want. And that should be easy. So we're getting x ln x minus x plus c. So it does work for problems like that as well. Okay. And I'm going to show you one problem where it gets a little tricky. Somewhat similar to this, but it does require for you to remember some formula. So the integral of our cosine x dx. I'm sure you know how to differentiate our cosine, but what about integrating that? So again, not my choice here. Our cosine x is going to be our u. The formula, if you remember that, it's negative 1 over square root of 1 minus x squared. Dx equals du, and then dx is going to be dv, which means x is v. Alright, of course, this is our last problem, but of course I saved the best for last. So uv, which is x times arc cosine x, minus the integral of negative x over square root of 1 minus x squared dx. So this is our integral of v du. And what we're going to do here is, I'm not going to work it out. This one can be done by using U-Substitution. I can just give you a hint. If you want, well, I don't want to use u because I already have u here. So what I can do, if you substitute 1 square root of 1 minus x squared, make a t. That's not the only possible substitution here, but that's one of the ones that you can actually use. You will be able to proceed from here and rewrite the rest of it with that. So this integral here, this one here, with the minus, is going to actually be a square root of 1 minus x squared. So it's going to be x times arc cosine x minus square root of 1 minus x squared, and then plus c. Okay? So hopefully it gives you an idea of how integration by parts is used for various problems, and you can kind of move on from here. And we'll see you next time.